It was 50 years ago this month that the U.S. landed the first 2 humans on the moon. Today on UC Davis Live, we'll mark the occasion with Sarah Stewart. She's a planetary scientist here at UC Davis, and this is her lab, where she uses these huge cannons to figure out how planets and moons form and evolve. We'll talk to her about that. We'll also talk to her about why it's a good idea to go back to the moon, and also how she came up with her new theory on how our moon formed, which garnered her a MacArthur Fellowship, which is also known as a MacArthur Genius Grant. I'm Satirius Johnson, and this is UC Davis Live. And here we are live with Dr. Sarah Stewart. Thank you so much for coming on.
Thank you.
And before we start, I just want to put out there that we are taking questions on the real science of the moon and on Sarah's work. So if you'd like to comment or ask a question, please just drop them into the comments section and we will try to work them in. So, we are in this exciting time right now. We're not only celebrating the 50th anniversary of the landing of 2 humans on the moon and bringing them back safe and sound. We're also looking forward to going back to the moon. So this is a really exciting time. Why do you think it's important for us to go back to the moon?
It is our nearest planetary neighbor, and we still don't understand many fundamental things about it. And so in terms of just basic planetary science, it entices us, but also we can go there and we can pick up rocks and bring them home. And so it's a great technological challenge and human adventure.
Mm-hmm. What did we learn when we went to the moon the first time around in the Apollo missions?
The rocks that we brought back were key to our understanding of the origin of the moon and its relationship to Earth. Before we had those rock samples, we didn't appreciate just how closely linked the Earth and moon really are.
And there are actually still some rocks that they brought back from the Apollo missions that they just sealed away and preserved, thinking that in the future we'd be able to examine them more closely or differently. So what are you looking forward to learning about? Like, what can we learn from those rocks that haven't been studied yet that we couldn't figure out back then?
So this was a brilliant idea to hold back some samples, knowing that technology would progress so that we could make better measurements. And so the analytic capabilities that we have now are tremendously better, and specifically on microanalyses, because we have very few samples and we want to glean the most out of them that we can. And so we're looking for fine differences in the isotopes of different elements. We're looking at micromagnetism and nanoimaging. It'll be fantastic to see.
And what kind of things can we learn from this new technology?
So we have since had several major missions to the moon, and we're trying to understand the structure of the regolith, of the surface, and how it evolved over time. And the spacecraft missions have led us to new questions about how the crust evolved that we will now be able to address by looking at these hand samples.
Okay, so let's get to your theory, your new theory about how the moon formed. Up until you came up with your theory, the kind of prevailing theory was the giant impact theory. Like, basically an object the size of Mars is the theory, hit the Earth, and then a piece of the Earth broke off and became the moon eventually. How did, I guess, why don't you just explain what your theory is and then how you came about coming up with that?
So the giant impact theory wasn't able to explain all the observations, which is why scientists were looking for other ideas about the origin of the moon.
So it explained some things, but not everything.
It could explain the size of the moon, the small iron core of the moon, the high temperature origin, why it's so dry. But it didn't explain why the moon was like a chemical twin to the Earth, because when we could model that Mars-sized impactor striking the Earth, we learned that most of the moon should have been made out of that body. And that body should have its own chemical fingerprint. So that was the ultimate conflict, was how to have a giant impact make a moon that was so closely related to the Earth. And we still begin our model with a giant impact, but what we learned is that most giant impacts transform the Earth into a completely different object that we named as synestia. This is a hot, vaporous version of the Earth that extends well past the orbit of the moon today, and we propose that the moon grew inside of this synestia vapor, and that's why the moon has the chemical characteristics of the Earth.
So the Earth was a solid planet. It was hit by this other large object. It vaporizes into this huge cloud, and in the cloud, the moon forms.
Yes.
Okay. And then eventually, I guess, the Earth forms.
So the synestia is a rock vapor outer object. The Earth is temporarily transformed into something more like Jupiter, more like a gas giant planet than the solid planet that we know today. But it isn't stable, so it'll cool down by radiating to space and turn back into a solid planet again.
Okay, so now how did you come up with this theory?
So it was an accident, of course, because that's how science works. And so we had proposed an intermediate idea, which was that a certain kind of impact, a special configuration, could make the disk around the Earth have the same mixture of the two bodies in the Earth and in the Moon. And that required a high energy impact that made the Earth spin faster. And we published that several years ago. And people weren't totally satisfied with the solution because it was a special case. And we would like a general answer for the Moon.
Right.
And so we were looking at, my student and I, Simon Locke, were looking at plots of our computer simulations. And we realized that we didn't have a normal planet surrounded by a normal disk. And so we literally remember this day, sitting in front of the computer where we had a Eureka moment and said, it's totally different. We have no idea what it is. And that set off a couple years of trying to figure out when is a planet and when is a planet a synestia and what's the difference.
So you had computer modeling. We also saw in the open, we were in your lab and we saw those huge cannons. How do you use the cannons to get to these kind of conclusions?
So the key to understanding the computer models is to believe them. And so we try to benchmark what the codes are doing with lab experiments. And so in the lab with our gas guns, we can recreate sort of little snippets of giant impacts. And think of it as one little parcel at a time. We can take a piece of rock, whack it with a strong shock wave, and measure what happens, how much vaporizes, how hot it gets. So in our computer codes, we try to verify that little parcels of rock go through that same thermodynamic path. And then we can try to believe our interpretations of the computer models because we can't recreate a whole giant impact in the lab.
Wow, okay, great. And how powerful are those cannons? I mean,
so we have two different cannons in the lab, and one can reach the pressures in the middle of Earth's mantle, and one can reach the pressures all the way to Earth's core.
wow, very powerful.
Yes.
That's amazing. So we are taking questions from you if you're watching right now and you'd like to ask Sarah Stewart anything about the Moon or about her work. We just drop them in the comments section and we'll try to work them in. I wanted to ask you, is it true that it's hard to find rocks here on Earth that are as old as the rocks that are on the Moon?
So Earth is an extremely geologically active planet. Plate tectonics is continuously resurfacing our crust. And so there are very few rocks that are older than a couple billion years age on the surface of the Earth. And the Moon, without having an active geologic cycle, has what we think of as its primary crust, the crust that formed when the Moon solidified from a magma.
Okay. So now your theory, the synestia theory, does it apply to just the Earth's moon, the formation of it, or can it apply to all the moons in around, sort of going around all the planets in our solar system? Is it a general theory, or can we just say we're pretty sure in this case this is how it happened?
So what we've learned by studying giant impacts in general between rocky planets is that most rocky planets that are Earth size or larger would experience a giant impact that would make a synestia. So we think it's an extremely common process that happened with many, many exoplanets and would help make moons around those planets.
Right.
We don't know yet, does it happen with gas giant planets or ice giant planets, and that's future work.
Okay.
Yeah.
Common, but not so common that we have to worry about something hitting us tomorrow.
So luckily we don't live in a time period in the solar system where there's still giant impacts.
Right, okay. So what's it like being the person behind such a kind of shift in thinking about how the Moon formed?
So I get to do all the most fun things that a scientist gets to do, right? I get to do crazy experiments, I get to have Eureka moments, and I get to change the way that people look at the universe. And so that has been so much fun, but I've done it with a team of people, right? My students and the colleagues in the field who poke us, who say, you really have to explain this observation. And it's not a done deal, right? This is a new theory, and people are still poking at it and testing it, and we're going to keep developing it and see how far we can take it.
I was going to ask you, are you still conducting research to kind of fine-tune this theory?
Absolutely.
Yeah.
I've been spending my days trying to build better models to believe more details out of these codes because we want to be able to test the idea.
Can you talk a little bit about how you're going about doing that? Like,
So one of the best ways to test the model would be to make chemical predictions about small differences between the Earth and the Moon, which is why these new samples analyses are so important. And to be able to do that, we really have to believe the pressure and temperature conditions under which the Moon formed, which means we really need to be able to describe that synestia quite precisely to make chemical predictions. So that's the part we're working on, that material model.
So it looks like we got a question from Bo, who's watching on Facebook. Why does the Moon not revolve around Earth
Right.
at the equator, which is the expected path of where it should be?
Right. So the giant impact theory, in any version, makes a disk of debris that should be in the equator of the post-impact planet. And our moon is tilted 5 degrees off of Earth's equator, which is why we don't have eclipses every month. And so it has been a big problem with the giant impact theory that the moon's orbit is tilted when it was predicted to be in the equatorial plane. So there were different ideas about torquing the moon's orbit after the fact, or maybe flybys of late planetary objects that torqued the moon's orbit. In our current proposal, we proposed that when the Earth formed, it was actually tilted over in its orbit more than today. So we have our seasons from our 23-degree tilt. But it's likely that the Earth could have been tilted even more over. And if that were the case, then there's a long evolution process that gets us to today. And we think that the moon's orbital tilt is left over from the processes that led from Earth's bigger tilt.
Okay, great. Robert from Facebook is asking, does the Moon have quakes like the Earth? Are there moonquakes?
Yes, we've measured them with
Oh,
the
really?
Apollo seismometers. This was one of the greatest successes of the Apollo missions, was that the seismometers detected moonquakes.
They were left behind.
They were implanted
Okay.
into the ground and then recorded and sent back signals for many years. And they measured 2 different types of moonquakes. One were formed by tides with the Earth. Those were deeper moonquakes. And some were detections of impacts onto the surface. And using those seismic signals, we could map the interior structure of the moon.
Oh, excellent, amazing. Here, another question from Facebook. T from Facebook is writing, I was wondering, what are the odds that another planet just like the Earth geologically exists? This is like the big question that everybody wants to know.
Everyone wants to find Earth-like planets. So what we know now from our studies of exoplanets is every star has multiple planets. Planets are an outcome of star formation. And now the big question is how many are Earth-like? And we see that there are small planets and large gaseous planets around all these stars. So we know that there's some group of rocky planets with thin atmospheres that we would call Earth-like. Now, how many have beachfront property, how many have life, is a much smaller sample, but they're out there. And we have candidates of Earth-like planets by that criteria having water and a thin atmosphere. And we're still looking for signals to tell us that there's life.
That's great, that's great. Let me ask you, when you came to UC Davis, you came from Harvard where you were teaching, and you brought those huge cannons with you. Can you give us a sense of how big they are? I mean, we saw video of them, but talk to us about how big they are, and then how did you actually have them move across the country?
Logistically.
Yeah, I mean,
I think we have pictures of the whole process because it's kind of crazy. I mean, moving them into Harvard in the first place involved cutting out part of a wall to get a space big enough just to bring them into the lab, because the lab was in the basement. And so cranes, large clearances measuring everything, but the small cannon's 6 meters long. The whole room is 84 feet long, and so it is a bowling alley of a space. And we need the length to accelerate projectiles to these high velocities. And the highest velocities we can get to would be over 7 kilometers per second.
Wow.
So, so we needed a complicated rigging system to get the guns one gun out of Harvard, and then we bought a second gun here. And by comparison, our loading dock here is quite nice. And
Right.
easy
Oh, that's
to,
great. But
install.
it sounds like it's a custom job all the way.
There's a great video of installing the guns that we have on campus. Yeah.
That's great. We have another question from Facebook. Jason is asking, does the moon contain water under the crust? If so, how much?
So, from spacecraft that have orbited the moon, we have mapped a signature for water, which is measuring the number of neutrons in the lunar crust. And so what we observe is that there are pockets of what we think are ground ice in the shaded craters in the poles. And there appear to be a lot. Now, detecting how much is difficult because we can only detect the upper layers, and so we
Right.
don't know how deep these water deposits go. But more spacecraft will be looking for them. The Indians are launching on the 15th another spacecraft whose purpose is to focus on polar ice deposits.
Wow, amazing. David from Facebook is writing, hi, I believe in the Big Bang, but how does it explain galaxies colliding with each other? Did they take left-hand turns or something?
So galaxy formation, there's a big group at UC Davis that studies galaxy formation and evolution. And so that's not my main theory.
Right.
But just like planets collide with each other,
I guess I was thinking
galaxies
there's a Big
interact
Bang.
gravitationally. I
Right.
mean, they're just interacting gravitationally, and the stars, the groups of stars in that case, are what lead to these galaxy-galaxy collisions.
Right,
But
right.
it's mostly gravitational influence from the dark matter and matter in those galaxies.
Okay. How did you become interested in planetary science?
I remember watching Star Trek as a child and just thinking this was the coolest
Yeah.
thing, and of course we should go to every planet in the universe and visit them and
Right.
send our probes. And so it just seemed like the natural thing that we would do. And I had exceptional high school physics and math teachers that really got me hooked on physics, and that set me down this path.
That's really great. Well, I was going to ask you, like, whether you had role models or mentors coming up. As a woman in science, it tends to be more of a male-dominated field, even today.
That's right. So I'm an Air Force brat. So I didn't know any scientists growing up, and so my high school teachers were the ones that I met, and they were very encouraging. And my high school physics teacher even taught a second-year physics course that didn't exist to four of us who were so interested in science that we came in crazy early mornings for an extra class.
Wow, that's
Yeah.
amazing.
So I had help, lots of early help and encouragement.
Great teachers.
Yes.
Amazing. That's really great. Linda from Facebook is asking, is there any valuable mineral that we can mine from the moon? Is there gold up there or something? Maybe diamonds?
Well, there are, just like there is on Earth, valuable. So these rare earth elements are present in the moon, and these are the things that people talk about mining from asteroids or mining from the moon. It's still expensive to mine, but they are present. And so when people talk about establishing a permanent base, they do think about the resources that are already present and how we could utilize them.
And so much of the
Yeah.
space industry has become privatized as well that could possibly be an incentive for SpaceX or some other private company to try to go up there.
There are several private companies serious about lunar exploration and able to do it, able to bring the costs down to do it.
It's realistic.
Yes.
Exactly. Andy from Facebook is asking, what are some of the chemicals that, if detected, would confirm your theory of moon formation?
So if we want to get technical, there are specific elements that are very temperature sensitive at the temperatures we think the moon formed. Silicon and oxygen, for example. And if we could predict the difference in isotopes of these elements between the Earth and the moon during our origin scenario, that would be extremely helpful. So there are directions that we're moving into. I will just admit they're very hard for us to do.
Yeah.
Yes.
Okay.
Yeah.
Omar is asking, why does the moon have no magnetic field?
The moon does not have a core dynamo today like the Earth does. Our field is generated by the motions in our core, but there is evidence that the moon had a field in the past. The rocks that we brought back from the moon, some of them are magnetized, and from spacecraft we've mapped what we call remnant magnetism, the leftover magnetism in the crust. And so there is evidence that the moon...
Interesting. what are you most looking forward to in our next missions? As we go back, we're planning to go back to the moon, say in 10 years from now or maybe later. What would you like to either happen or have
Right.
brought back, or?
Everyone wants samples from deeper down. We went to the near side of the moon, and most of the rock samples were either from the Mare basalts, the younger eruptions, and a few from the highlands. But to answer some of these bulk chemistry questions about the moon and understand its evolution, we're all targeting deep samples, which is why people are very interested in the big crater on the far side of the moon.
Interesting.
Called South Pole Aitken. Yeah.
So how does it work? Do you get to make requests for what you want, or is it just generally there's a consensus basically?
There have been broad consensus that was there and just recently turned off. Landed in South Pole Aitken and detected minerals that appear to be from deeper down. And so there have been missions proposed, like in the Discovery class missions, to go to South Pole Aitken and bring back samples. So it's a competitive process
Yes.
for scientists to propose and win missions, and it's just in the mix with everything else.
That sounds great. Robert from Facebook is asking, what's the catalyst used by the cannons to accelerate objects in your cannons?
So we use both gunpowder, just reloading powder that
Okay.
people use at home, as one of our propellants, and then we use compressed hydrogen or helium as a propellant. And compressed hydrogen it leads to our fastest
I
accelerations.
see. And I saw when we were in your lab, we saw signs for lasers in use. I guess you're using lasers.
So lasers are used to measure the velocities and of the projectile, and then the motion and the samples.
So what are you hoping will happen once we go back to the moon?
One, I hope we continue to send people into space. I still have that Star Trek girl in me that says I would love to see people go through the whole solar system. It's extremely challenging. I would love to see humans go to Mars. And that's just the spirit of exploration in me. In terms of the science of the moon, I agree. I would love to have these deeper samples. I'd like to know how much water is in the moon and how it got there, whether it was part of moon formation or whether it was delivered later by impacts that happened later in the moon. Yeah.
Interesting. Now, we have a couple of questions about your thoughts on mining metals such as gold and others that could change the Earth's magnetic lines of flux. Is that something we can talk about?
No, I don't think so. I don't think we're talking about a concentration of precious metals enough to do anything to the magnetic field. Yeah.
Okay. Well, Sarah Stewart, thank you so much for coming on. This has been an amazing talk. It was
Thank
really
you
great to
very
speak
much.
with you
It's
about
been
your
great.
work. And thank you for your contributions to science and everything else. Sarah Stewart is a MacArthur Fellow and planetary scientist at UC Davis. If you have any additional questions, please drop them in the comments section, and we'll try to get back to you with some answers. This is UC Davis Live. I'm Satirius Johnson.